Today we would be looking at a very interesting law, the next law after Boyle's law, and that is the Charles law for gases. Okay, so we are looking at gas laws, and this is the second one. Charles law says that the ratio of volume and temperature, it remains constant. Okay, so very simple law. And here we have a demonstration of the Charles law. There is a gas trapped inside this container. What I am doing is that I am only changing the temperature of the gas by reducing or removing this flame. I am only changing the temperature of the gas. The mass and the pressure is not changed, and the mass of the gas is not really changed, and only thing we are changing is temperature. At the various temperature I measure the volume, and if I plot that volume with temperature, it would come out to be the straight line, which means that the ratio of V and T, it remains constant. That is essentially the Charles law. In those times, Charles actually did an experiment, and using that experiment he was able to determine this law. And the experimental setup was very simple. It is as shown here. There is this oil bath. Okay, it is a beaker filled with oil, and in this oil bath, so this is oil, we have placed a capillary tube which is partially filled with air. Okay, so there is air here in the white region. There is air. Okay, in this region there is air. So this is a very thin capillary tube. And why do we need thin? Because even the small change in volume would produce a large change in height, because the tube is so very thin. Okay, so this is a very thin capillary tube. I can measure the volume of air which is trapped here by using this scale, and I can also measure the temperature of the oil bath using this thermometer. Okay, so there are two things I can measure. I change the temperature of the oil bath, I measure the volume of the air in capillary tube. Very simple experiment, and then I plot those values. Now this is what this is original values which were plotted by Charles, and these are actually the points that he obtained. Now these points he joined together. Okay, and then he said that, oh, because I can draw a straight line, therefore there has to be a linear relationship, which means that the temperature and the volume, their ratio all remains constant. Okay, so this is what he did. Now Lord Kelvin, he observed that if I extrapolate this graph backwards, okay, so I am extrapolating this graph backwards, then this line would intersect the x-axis. Okay, on the x-axis we have temperature, would intersect the x-axis at minus 273 degrees Celsius. So what does that mean? It really means that at this temperature, if it were possible to take the gas to this temperature, theoretically its volume would become zero. Of course, we know that much before this temperature is reached, the gas would become liquid, and so on and so forth. But if I extrapolate this graph backwards, the zero volume is attained at the temperature of minus 273 degrees Celsius. So this was the Lord Kelvin's observation, and he then repeated the experiment with several other gases, and he found out that, okay, this minus 273 degrees Celsius is what we now know also as 0 Kelvin, is actually a point at which volume of all the gases, not just hydrogen or helium, but all the gases, it reaches, theoretically it would reach zero. Okay, so absolute zero, the volume becomes zero for any gas. Okay, so all the lines would start from here. Okay, that is the one thing that we have to remember. The second thing, the graphs we have to observe, we have to remember, is that these are the graphs of the temperature and volume, but at different pressures. So as I increase the pressure, okay, so pressure is increasing downwards. Okay, as I increase the pressure, at the same temperature my volume actually decreases. Okay, that is to be expected, because I am pushing the gas down, I am trying to compress it. So at the same temperature my volume would actually decrease, and that is of course what we also would expect from Boyle's law. Okay, so from Boyle's law we know that P1 V1 is equal to P2 V2, or pressure and volume, they have inverse relationship. So at the same temperature, if I increase the pressure, my volume would decrease, and that is also shown in these plots. Okay, but at all the various pressures, the volume and temperature graph, it is a straight line. All of these three are straight lines. Okay, so these graphs are important because often questions are asked on this graph. Now the Charles law is actually so accurate that by using the volume of gases we can actually measure the temperature. and that is the principle of gas thermometers. Okay, and gas thermometers are more accurate than the mercury thermometer. So the Charles law is so very accurate, that the straight line is so very straight, that we at very accurate applications we use gas thermometers instead of using the mercury thermometers. Okay, so with that, we have understood what Charles law is. Now let us also look at some of the common examples that we see in real life where the Charles law actually applies. Okay, so on the various pressurized cans, for example, if you have used the pressurized can for painting, okay, for drawing the painting, or other pressurized cans, for example, the perfume cans that we have at home, or the insect repellents, okay, all of those are pressurized cans. In all of that, if you see, there is a warning written: do not keep away from direct sunlight. Okay, so there is that warning written. And why is that warning written there? Because the cans are already pressurized. If I increase the temperature of the can by putting it in sunlight, what would happen? The volume would increase and the cans could possibly burst. Okay, so that is the reason why we have that warning there. Okay, that is the another example of the Charles law is actually balloon. If I increase the temperature, its volume decreases. On the other hand, if I were to put it in ice, the volume would actually decrease, because the volume is directly proportional to temperature. So if temperature decreases, my volume decreases. Now, one of the things that we really have to understand here is that when we are using this formula, okay, when we use the volume and the temperature formula, and we would be doing numericals, so that will become more clear. V1 by T1 is equal to V2 by T2. What you have to remember when you use this formula, that this T1 and T2, the temperatures, they are in Kelvin. Okay, so don't use centigrade or Fahrenheit temperatures. Convert them to Kelvin and then do the numericals. Okay, so numericals, and these we would be discussing in the next class, in the subsequent class. Simple numericals, try to solve them yourself. If you are not able to solve them, then do not worry. We will actually be solving these numericals in the next class. Thank you very much.